Yep. All right. Moving along here, we're going to do slope fields today. So slope fields kind of a interesting topic. Probably could have done this before we solved differential equations. In fact, a lot of textbooks do. We decided to go in reverse order. So what is a slope field? So it has to do with differential equations. So let's take a look at a differential equation. dy dx equals x plus 1, right? So it's a differential equation. It's got an equation. It's got a derivative in it. It's a differential equation. Also notice that this one happens to be solved for the derivative. As you know, all differential equations don't need to be that, but this one is. And when we do slope fields, we're going to want to get that. We're always going to want to get dy dx to one side. And the reason for that is because we're basically going to do a plotting of slopes. So in other words, we're going to make like a field of slopes. So what the heck does that mean? Well, let's look at this grid here. And these can get annoying pretty quickly, so we're not going to go too far up. So we got 1, 2, 3 in this direction. We'll do 1, 2 in that direction. -1 in that direction, -1 in that direction. So now envision basically a grid here. So you have the point 0, 0, 1, 0, 2, 0, 3, 0. But then you have the point 0, 1, 1, 1, 2, 1, 3, 1. So I'm basically just looking at a grid, almost like Battleship, if you guys even know what that is, of points. And what I want to do now is I actually want to plot slopes at each one of these points. So you're like, well, how would I do that? So take the point 0, 1, for example. If I take the point 0, 1, that's the x value, that's the y value. It looks like the slope at 0, 1 would be 0 plus 1, right? If I substitute that in, which is 1. So I'd get a slope of 1. So at the point 0, 1, I'm going to draw a slope, right? That has that's a short little line segment indicating a slope of 1, right? And how do you know it has a slope of 1? Well, because I'm pointing to this point, right? Up 1 over 1. So you draw a short little line segment with the slope. Take 0, 0, for example. If I plotted the slope there, well, again, the x is 0. So 0 plus 1 is 1. So short little line segment, slope of 1, right? And you might even notice that if I take any point on the y-axis, right, since y is not in the formula for the slope here, it's always going to be the same because the x value is 0. So all of these slopes are going to be 1. And now I'm going to do that for all of the other grid values, right? So let's take this point right here. This is the point 1, 0, right? Remind myself that's the x, that's the y. So if I plug it into that derivative, I'm going to get 1, because that's the x value, plus 1 is 2. So now I have to draw a slope that indicates a line segment, or I'm sorry, a line segment that indicates a slope of 2. So if this is my point, up 2 over 1, I should be aiming for that. So it's just a little steeper. And just like the other guys, these are all going to be the same. Now, don't always think they're all going to be the same. They're only the same because my differential equation is strictly in terms of x. So the y value is not affecting the slope. If there was a y in this, then you'd have to do an individual slope for each grid. So we're kind of getting lucky that it's just an x, right? Come over to the values of 2, right? So 2 plus 1 is 3. So this will be a little steeper, right? Come over to the values of 3. 3 plus 1 is 4. These slopes will be a little steeper, right? That one's a little off, but you get the idea. Come over to -1. Now, this is kind of interesting. When you plug -1 in for x, right, because all of the points on this line here have an x value of -1, those slopes would be 0, right? And that's what you get. And so this right here would be the slope field for this differential equation, dy dx equals x plus 1. So at first glance, you're like, what in God's name is that? What is that giving us? Well, first let's do this, because as you see, it's kind of annoying to do these by hand. So let's bust out some technology. All right, so we're going to go to the GeoGebra world today. Okay, so here I have a slope field drawn for the same differential equation we were just looking at, dy dx equals x plus 1, but I drew it at a lot more points. So it kind of, has a little bit more flow to it, right? The cool thing about this is I can draw it tighter and tighter. So in other words, I can use more points, more grid points, And the more I do, the kind of clearer picture I get of what's going on here. So that's a slope field that's pretty dense because there's lots of short little line segments, right? And you can almost kind of see a pattern there. Whereas one that's not as dense, right, might look something like this, and it's kind of tough to see the pattern. So obviously, the more values that you can plot, the more slopes that you can plot, the better picture you're going to get. But the question is, what is this a picture of, right? If you can figure that out, I'd be super impressed. So let's go back to what we've been doing. So now what have we been doing with these things? We've been solving them. So let's go ahead and solve them. All right. So how would I solve this? You guessed it, separation of variables. So there is no y. So the dy is good where it is. It's on the left side. So that's all good. I'd have to multiply both sides by dx, and I'd end up getting this. And don't freak out because you don't see anything other than dy. It's like 1 dy, right? So both sides now are in a Riemann integrable form. So I got the green light to integrate the left side, integrate the right side. Integral of the left side is going to be just y, right? Integral of the right side, integral of sum of the integrals. It's 1/2 x squared plus x. Remember, if you left it like this on the AP test, you'd get hammered because what did you forget? Duff? No, Duff. Good try, but that's not correct. Liam? Yes, Liam. Constant of integration. Good job, Liam. Okay, so this is what you get. So now what is this thing? This is a family of functions differing by a constant that satisfies this differential equation. So look at this family of functions. You know what the graphs of these things look like, right? What are those? Those are parabolas, right? So you're like, oh, so let me go back to that slope field. Nope, no, I won't go back to that. Let's go back to, we got it, this. What do you kind of see kind of embedded in this slope field? You should see curves. You should see parabolas. So like maybe if I drew in a particular solution, one that went through 2, -1, right? There's a parabola, right? Maybe if I draw in this guy, turn off that guy, there's a parabola. That's a little bit of a weird point, right? What about this guy? What about those guys? These are all particular solutions going through specific points. When I just look at the slope field, what am I looking at? Yeah, I'm looking at the family of solutions differing by a constant. All right, so let's go back to this guy, this particular one. This goes through the point 2, -1. If you're not following me, let's actually find that. All right, so we'll go back here. Let's pretend like this was an initial value problem now. So dy dx equals x plus 1. So that's my differential equation. And now the point 2, -1 is maybe our initial value. So let's use that to solve for c here. So if I go ahead and do that, this is my x, this is my y. -1 equals 1/2 2 squared plus 2 plus c. So this is going to be 2 squared is 4, divided by 2 is 2. 2 plus 2 is going to be 4. So you get this. Subtract that over. You're going to get c equals -5. So now a particular solution would be y equals 1/2 x squared plus x minus 5. Right? So whereas when you were looking at the slope field, you were kind of visualizing this. And then when I clicked that little button and you saw that one solution, you were visualizing this specific parabola. All right, so let's go back to that. Okay, this guy right here, it's kind of tough to see. If I scroll down, right, you can see it would intersect down below at -5. It's just not in the grid. But this is the particular solution that goes through the point 2, -1. Right. So in layman's terms, what is a slope field? It's just a visual of the family of solutions differing by a constant. All right. So that's actually kind of neat that you can get that really, if you think about it, without any calculus, because all you're doing is plugging values into an equation and plotting short little line segments, right? You could have probably done this in 8th grade without knowing any calculus because you knew how to plot points. So that's actually kind of powerful. Because if you remember me saying, differential equations are not always easy to solve. In fact, a lot of times they're very difficult to solve. Separation of variables is a technique that's very limited. So they can be difficult, but making a slope field is not difficult, right? If you know how to plot points, you can make a slope field. And so you can get a really good idea of what the general solution is going to look like by creating a slope field. Okay, so once again, a slope field is just a visual of the family of functions differing by a constant. All right, so that's actually kind of neat. All right, so I'm going to stop this video here and then I'll get back at it in a second.